Hi, I'm Mari, and I lead the content team at Datacamp. We are an international team of data scientists, analysts, statisticians, programmers, and much more. Data science is a dynamic field. The tools that we use and the capabilities of our teams are changing every day. In this course, I'll explain what data science is and how you can use it to strengthen your organization. If we Google, "What is data science?" we'll see a huge amount of confusing information. But data science is actually simple. It's a set of methodologies for taking in thousands of forms of data that are available to us today and using them to draw meaningful conclusions. Data is all around us. Every like, click, email, credit card swipe, or tweet is a new piece of data that can be used to better describe the present or better predict the future. So, what can data do for you and your team? Data can describe our current state. This can be accomplished with dashboards or alerts, simplifying time-intensive reporting processes with new data technology. It can help detect anomalous events. If we have data on what has happened previously, we can increase efficiency by automatically detecting a new event that is unexpected. Data can also diagnose the causes of observed events and behaviors. Rather than determining correlations between small numbers of events, data science techniques help us understand complex systems with many possible causes. Finally, data can predict future events. We can use new techniques to take various causes into account and predict potential outcomes. Further, we can evaluate the probability of our prediction mathematically to clarify our level of uncertainty. So now we know what data science is. The next question is, why is it so popular? The answer is pretty banal. We're collecting more data than ever before. Suppose that you visit a car dealership and fill out some information. All of that data is automatically entered into a computer and combined with the data from hundreds of dealerships into one big database. Once we have that data, it's easy to use the email address that you provided when you bought that car to tie your car purchase data with your data from social media or web browsing. Suddenly, we have a very complete picture about everyone who purchased a car in the last year: their ages, their likes and dislikes, their friends and family. This additional data can be used to predict what price you can pay for your car, what other purchases you're likely to make, or how best to sell you insurance for that new car. Data is everywhere, and it is incredibly valuable for businesses. So how do we start to use our data? In data science, we generally have 3 steps to any project. First, we collect data from many sources, such as customer surveys, web traffic results, emails between sales representatives and potential clients, and financial transactions. Next, we explore and visualize our data. This could involve building dashboards to track how our data changes over time or perform comparisons between 2 sets of data. Finally, we make predictions with our data. For example, this could involve building a system that segments customers or classifies pictures of different types of cars. Now you know why data science is important to business and the first 3 steps in the data science workflow. Let's explore these themes in some practical exercises. Previously, you learned the definition of data science and the steps in a data science workflow. In this lesson, you'll learn how to apply data science to real business problems. Let's take a deep dive into 3 exciting areas of data science: traditional machine learning, the Internet of Things, and deep learning. Suppose you work in fraud detection at a large bank. You'd like to use data to determine the probability that the transaction is fake. To answer this question, you might start by gathering information about each purchase, such as the amount, date, location, purchase type, and cardholder's address. You'll need many examples of transactions, including this information, as well as a label that tells you whether each transaction is valid or fraudulent. Luckily, you probably have this information in a database. These records are called training data and are used to build an algorithm. Each time a new transaction occurs, you'll give your algorithm information, like amount and date, and it will answer the original question: what is the probability that this transaction is fraudulent? Before we can answer that question, let's walk through our example and highlight what we need for machine learning to work its magic. First, a data science problem begins with a well-defined question. Our question was, what is the probability that this transaction is fraudulent? Next, we need some data to analyze. We had months of old credit card transactions and associated metadata that had already been identified as either fraudulent or valid. Finally, we need additional data every time we want to make a new prediction. We needed to have the same type of information on every new purchase so that we could label it as fraudulent or valid. Now, suppose you're trying to build a smartwatch to monitor physical activity. You want to be able to auto-detect different activities, such as walking or running. Your smartwatch is equipped with a special sensor called an accelerometer that monitors motion in 3 dimensions. The data generated by the sensor is the basis of your machine learning problem. You could ask several volunteers to wear your watch and record when they are running or walking. You could then develop an algorithm that recognizes accelerometer data as representing one of those 2 states, walking or running. Your smartwatch is part of a fast-growing field called the Internet of Things, also known as IoT, which is often combined with data science. IoT refers to gadgets that are not standard computers, but still have the ability to transmit data. This includes smartwatches, internet-connected home security systems, electronic toll collection systems, building energy management systems, and much, much more. IoT data is a great resource for data science projects. Let's tackle another example. A key task for self-driving cars is identifying when an image contains a human. What would the dataset be for this problem? We could express the picture as a matrix of numbers where each number represents a pixel. However, this approach would probably fail if we fed the matrix into a traditional machine learning model. There's simply too much input data. We need a more advanced algorithm, known as deep learning. In deep learning, multiple layers of mini algorithms called neurons work together to draw complex conclusions. Deep learning takes much, much more training data than a traditional machine learning model, but is also able to learn relationships that traditional models cannot. Deep learning is used to solve data-intensive problems such as image classification or language understanding. You're now familiar with several different applications of data science. Let's practice. In this lesson, you'll learn how to build and structure your data team to meet your organization's needs. You might be surprised to learn that data science isn't a single field. It's actually 3 different jobs: data engineer, data analyst, and machine learning scientist. Let's explore each one. Data engineers control the flow of information. They build specialized data storage systems and the infrastructure to ensure that the data is easy to obtain and process. Most data engineers are very familiar with SQL, which they use to store and manage big data. They also use one of the following programming languages like Java, Scala, or Python to process data and automate data-related tasks. Data analysts describe the present via data. They do this with dashboards, hypothesis tests, and visualization. They often have some background in statistics or computer science, but tend to have less engineering experience than data engineers and less math experience than data scientists. Data analysts use spreadsheets to perform simple analyses on small quantities of data. They use SQL, the same language used by data engineers, for larger analyses. While data engineers build and configure SQL storage solutions, data analysts use existing databases to consume and summarize data. Analysts also use business intelligence, or BI, tools such as Tableau, Power BI, or Looker to create dashboards and share their analyses. Machine learning is perhaps the buzziest part of data science. It's used to extrapolate what's likely to be true from what we already know. These scientists use training data to classify larger, unrulier data. Machine learning can tell us how much money a stock might be worth next week, which images contain a car, or what sentiments are expressed by a set of tweets. Machine learning scientists use either Python or R to create their predictive models. Both are great programming languages for data science, and a candidate who knows one language can likely read code in the other language. Remember, programming languages aren't as difficult to learn as spoken languages. If someone knows how to speak French, it might take them years to learn to speak German. Programming languages are more similar to power tools. If you know how to use a power drill, you don't necessarily know how to use an electric saw, but you can probably learn with a little training. To recap, data engineers store and maintain data. Data analysts visualize and describe data. And machine learning scientists model and predict with data. Each position uses a slightly different set of tools to achieve their goals. Once you've hired some data professionals, there are three main ways you can structure your data team: isolated, embedded, or hybrid. An isolated data team can contain one or multiple types of data employees without any other teams like engineering or product. This is a great structure for training new team members and quickly changing which project each member is working on. Alternatively, it can be helpful to use an embedded model where each data employee is part of a squad, which also contains engineers and product managers. This model lets each data employee gain experience on a specific business project, making them a valuable expert. The hybrid model looks similar to the embedded model, but with an additional sync for all data employees across all squads. This additional layer of organization allows for uniform data processes and career development, regardless of which project an employee is assigned to. You're now familiar with three key data team members and three types of team structures. Let's practice.